In the last couple of concepts, we've been talking about output privacy. Within an information flow, output privacy refers to a guarantee that certain attributes about the input can be impossible to reverse engineer if you have access to some portion of the output. We then introduced the concept of differential privacy, a form of output privacy guarantee which can make it, very difficult to reverse engineer individual people's contributions to an aggregate statistical result, like a sum or mean or median or mode. And we finished the last concept with an example where we designed an information flow to calculate the average age of the students of this course. And we did so in a way which ensured that I couldn't use the average age to reverse engineer the ages of specific students. And we did this by asking each student to add a random number between -100 and 100 to their age before submitting it to me, so that when I averaged everyone's ages together, all the noise canceled out and I got a reasonably accurate estimate. But if I tried to reverse engineer anyone's true age from the aggregate, the most I could ever learn was the very noisy submission that any particular student made to me, but not their true age. And in this last section, while intuitive, was still a little bit imprecise. And a slight modification of the example will immediately show why. So in the example, I suggested that each student would add their age with a random number between -100 and 100. But what if I had said that the random number should be between -2 and 2? Well, that wouldn't have been a particularly great privacy protection, right? While I wouldn't know your exact age, I would have a pretty good idea if I'm only given a 5-year range of randomness that you're adding to your own age. And what if I had said to add a random number between 0 and 1? Like, that's basically no privacy protection at all. So it seems that this guarantee of output privacy isn't quite the guarantee we might have expected at first. Like, it's not a totally binary guarantee. It's actually sort of more of a degree of protection, right? And the more randomness that people add to their own data, the less I know about your age, the better the privacy protection. So without getting into the math too heavily, one of the most important concepts in differential privacy is the way in which it helps us measure the difference between a really strong privacy guarantee and a weak one. And in our example, this is the ability to measure the difference between using random numbers between -100 and 100 and using random numbers between 0 and 1 to protect your age. This measurement in differential privacy is called epsilon. Think of it this way. Let's say you're a medical research center and you've got a lot of data, about say 3,000 patients, and you want to let outside researchers and PhD students and all sorts of people try to use your data to, say, cure cancer. But you're concerned that if you didn't do it properly, they would be able to reverse engineer, their statistical results, maybe a machine learning model or a big graph or histogram into some of the input medical records. How do you prevent this? Well, the way you prevent it is by giving each researcher what's called a privacy budget. A privacy budget is a measure that says all of your aggregate results that you generate from my data must, when taken together, represent less than X epsilon of information, meaning that X is some measure of your maximum tolerance for information reconstruction risk. So if you weren't too worried about people trying to reconstruct data, you might set the epsilon budget to be, 100. But if you're really worried, you might set it to 1 or maybe even just 0.1. And this works because no matter what algorithm they decide to run on your data set, as long as it can be measured by epsilon, you get a formal guarantee about the probability that a researcher could reconstruct your private data from their statistical results. Pretty neat, right? But this isn't the end of the story. If you were listening closely, you might have noticed that I said every researcher gets their own privacy budget. Every researcher gets their own epsilon. So if you had 10 researchers, they were all studying, your group of 3,000 patients, and each one of those 10 researchers had a privacy budget of, say, 20 epsilon, then wouldn't that mean that something like 200 epsilon of private information is potentially going out your door? So what happens if researchers share their results with each other? Well, in theory, if two researchers each had 20 epsilon of privacy budget, and they combine their results in just the right way, they could achieve as much information leakage as if you had given someone 40 epsilon. That's a problem. Well, not necessarily. You see, epsilon is just a measurement. You can either measure epsilon across a data point's entire lifetime, or you can measure it for each scientist that works with it. So if you're worried about people publishing their results, on the open internet, then you should probably be keeping track of a global epsilon across all research, like a global privacy budget across all researchers who work with your dataset. But if you're working with researchers who aren't likely to be sharing their information, anywhere or with each other, then researcher-specific epsilon, researcher-specific privacy budget is probably fine. Now, finally, we want to poke and prod this sort of notion of privacy budgets one more time. And in the first scenario, we considered using epsilon to limit the amount that a single researcher could learn from your data set, right? So in the second scenario, we considered what would happen if multiple researchers are going to share their results with each other, potentially pooling their knowledge to leak information from your data set. But in this last scenario, I don't want you to think from the perspective of a dataset owner. I want you to think from the perspective of a patient in this medical dataset. So if you are a patient, how does epsilon apply to you? So let's say you're one of the people in the dataset from the previous example, and so the hospital decides to allow a global epsilon privacy budget across all researchers, right, studying data about you of 20 epsilon, meaning all the people who are going to study the data set that you are present in, the sum total of all their epsilons must forever be underneath 20 epsilon. There's 20 epsilon for all researchers to share. That guarantee is made to you and to everyone else in the data set with you. So if there are 10,000 people in the data set, they all get to sleep well at night, knowing that no more than 20 epsilon of their personal information will be, running around throughout society. But what if you're actually a patient at two different hospitals, and both of those hospitals let students from a local research university study their patients? Well, then am I sure that I can sleep well at night? Am I sure there's only 20 epsilon running around about me? Well, if there's 20 epsilon from each hospital and I'm present in both data sets at both hospitals, then no. There could be 40 epsilon of private information running around about me. And what about other hospitals? What about my dentist? What about my eye doctor? Should these be included as well? Like, are they all spending my epsilon at the same time? Okay, so we've gotten pretty deep into this, and you might be wondering, do I really care about this? Is epsilon really that big of a deal? So here's the thing. Just because your hospital doesn't think they're leaking private information about you doesn't mean they're not. And not because of anything they're doing, but because of other information that might be able to help fill in the gaps that your hospital is intentionally not releasing. Let me give you an example. So I imagine you're probably familiar with Netflix. Maybe you watch it every night, right? Netflix used to run one of the largest machine learning competitions in the world, a challenge that was called the Netflix Prize, where machine learning researchers from all over the world would compete to build the best movie recommender ever, right? Sounds pretty cool. So to facilitate the competition, they took their, big list of movies and their records of who had liked or not liked what movie. And they released that data set. But before they did, they replaced all the movie titles with random numbers. And they replaced all the usernames of people, right, with random numbers. So it was just a big blob of movie ratings between, anonymous people and anonymous movies, right? Well, it would have been if IMDb hadn't existed. You see, IMDb also was keeping a big list of movies and a big list of users. And occasionally, people would post on IMDb and rate a movie that they had also rated on Netflix. And because this IMDb dataset existed, some very clever researchers at UT Austin were able to use IMDb to reverse engineer and de-anonymize the seemingly anonymous Netflix movie reviews in the Netflix dataset. Put in differential privacy terms, because Netflix released some epsilon, and IMDb had already released quite a bit because it's a public website. So much epsilon was out in public that these researchers were able to successfully launch a de-anonymization attack. Now, fortunately, the movies you rate isn't the most sensitive information in the world, but the same kinds of attacks have happened with anonymized medical records, anonymized browsing history, even de-anonymizing the medical records of a prominent US congressman and the not-so-nice browsing history of a European judge. The amount of epsilon running around about you is a measurement of the probability that if someone had access to all the scientific research or products or services that were being released with information about you in it, it's the probability that they could reconstruct facts relating to you specifically. All that is to say, epsilon is your protection. It's a formal upper bound on the probability that bad things could happen to you if you participate in a statistical study. And by statistical study, I mean in a very generic sense. You might not be like a formal survey, but any type of statistical analysis. And you might be thinking, well, I don't really participate in surveys, but every time you use Chrome or Firefox or an Apple computer, you're participating in statistical studies which use differential privacy to protect you. These companies study how their software is used so they can spot bugs and generally just improve their software. Even when you use certain health monitoring apps, your information may be aggregated. When you text and your texting app tries to help you by predicting the next word, the software that learns how to do that is actively learning, not just from your text messages, but from the text messages of everyone else who has a phone like yours. And when you go to bed and you plug in your Android or iPhone, a new updated version of that software learns from your texts, goes up to the cloud, is aggregated with millions of other updates, and the new smarter version comes down to your phone. And you are protected in all of this using differential privacy, measured by some degree of epsilon. Another question you may have is, what level of epsilon is considered safe? We asked a privacy expert and differential privacy pioneer, Aaron Roth, what he thought about this. And here's what he said.
Yeah, so there's no universal answer to this, and it is a tricky question. There's a couple of ways to think about it. And the ways to think about it sort of go back to different ways you can pose the definition. So first of all, one way of thinking about differential privacy is it talks about what advantage all-powerful adversary who knows everything else about the world can have in guessing whether the result of the analysis he has seen was the result of running the analysis on a data set that had your data compared to running the analysis on the data set that didn't have your data. What advantage the adversary can have over random guessing. So in this world where the adversary knows everything about the data set other than whether your data is in it or not, right? There's only two possible options. And by random guessing, you can get the answer right half the time. And differential privacy says roughly that he shouldn't be able to get the answer right with probability, substantially more than, like e to the epsilon times 1/2. Now, when you think about the definition in this way, then epsilon equals 5 doesn't make any sense. It offers, basically a vacuous guarantee. And so when you think about it this way, you really have to, like the only sensible values of epsilon are values of epsilon that are, 1 or less. Now, there's another way of posing the definition of differential privacy, which is that it is saying that whatever event you're worried about, whatever thing you're scared of, this could really be anything. Maybe you're worried about being denied health insurance, or you're worried about getting annoying phone calls during dinner. That event is almost no more likely to occur if your data is used in an analysis compared to if it's not, where almost no more likely means the probability has increased by an e to the epsilon factor. Now, in this view, and by the way, this is the same definition, but in this view, how big a reasonable value of epsilon is depends on how unlikely the thing that you were scared of was to occur if your data wasn't in the data set, right? Because even if e to the epsilon is a relatively big number, e to the epsilon times the probability of the bad event, if your data was not in the data set, might still be a small number. And so if the thing that you are concerned about was some very, very specific disclosure, that like your password, your social security number would be revealed, then epsilon can actually be like reasonably large and still offer a meaningful guarantee.
See, here's the way to think about epsilon. We can transform epsilon by calculating e to the power of epsilon, and we'll call that beta. And if you don't know what I mean, don't worry about it. I'm just transforming epsilon into a more useful number called beta by running it through a function. Now I'm just going to refer to beta, which is just epsilon run through this function, okay? So let's say you're deciding whether to participate in a medical study. And the medical study guarantees that no more than 2 beta will be released, which is roughly 0.7 epsilon, if you're keeping track. So if no more than 2 beta will be released, you might wonder to yourself, 2 beta, is that too much? Here's the magic of differential privacy. You ready? Here it is. If beta is 2, then you can pick any event in your future. Any event that you're worried about, your insurance premiums being raised, your partner leaving you, your car spontaneously combusting, any event, right? And beta will guarantee that if you participate in this medical study, the most that the probability of that event would go up is 2 times the current probability. So the probability of your insurance premiums going up was 0.2%. Now they're at most 0.4%. If the probability of you getting eaten by a wildebeest is 0.0001%, now there's definitely no more than 0.002% chance. And you're like, what the heck, wildebeests? What does that have to do with this medical study? Why is that relevant? My point is that from the perspective of differential privacy, the guarantee does not care about whether the event seems related. Differential privacy is constructed in a way that no matter what the event is, the probability that the event will happen will be no greater than beta times the current probability after when you participate in this study. Now, if the events are totally unrelated, like wildebeests, then maybe the probability won't change at all, right? But what differential privacy is saying is that after participating in a statistical study, the new probability won't be greater than the old probability times beta, and then beta will always be 1 or greater. So take a moment, let that sink in, really simmer in that idea for a moment, because it's really, really powerful. And before we close, let's recap. We covered a lot of ground in this video, so I just want to review. First, we learned about the concept of a privacy budget and how it can be used to provide a strict upper bound on how much someone can learn from a private data set. Second, we learned about several variants on the idea of privacy budget. Maybe epsilon is measured per scientist, right? So that each scientist studying a data set has their own privacy budget. But we also noticed that this can cause problems if scientists start sharing information with each other or posting their results online. So we thought of another way to do privacy budgeting, a global privacy budget, which all scientists have to stay under. Finally, we considered the same concept from the perspective of a patient in the data set, and how there might be people spending epsilon about multiple data sets they're involved in at multiple different institutions, and how if someone went to all these institutions, the epsilons can really start to add up. And finally, we learned about how to really interpret epsilon as a privacy budget parameter. And we did this by translating epsilon into beta, which is basically just much more intuitive, like beta, which we can multiply by the probability of any event in our future and get a guarantee that after we participate in a statistical study, the new probability of those events won't exceed the old probability times the beta. It's a lot to take in, let it simmer, and when you're ready, I'll see you in the next concept.
Hi, I'm Roshan on the research team at OpenMined. Hope you enjoy the course.